So if you now open day 2, number 4, mixture models. Yes, go ahead.
I just want to make sure I'm putting this in the proper context. So what we're doing here is we're kind of pulling out some of these metrics that we know are going to influence whether or not we detect individuals in the field.
Yes.
And then we're going to be able to use these numbers that we're pulling out to essentially assess what sort of our range of detectability is.
Mm-hmm.
Is that kind of where
Yes.
we're going with all this?
Yes. And the next thing I'm going to skim over, maybe I'll just show the HTML so that you see conceptually what that means, but then I jump to the population estimation so that we can use this estimate that we've got and see how we can use this to make an adjustment. And one thing I didn't talk about in this C multi, when I said multinomial, that part is now clear. We have these bins, and that's why it's multinomial, because we really do those counts to some probabilities. But that C, conditional, what that means is when we are looking at the Tennessee warbler data, we have the total counts like this. There's a bunch of zeros. We detected nothing. So this estimation that we do here, which is described at the very end of this 2-3 file, is only looking at data where the sum is greater than 0. And by doing this, we are conditioning on y being greater than 0. And as a consequence, because we assume there is no error like false positives, so we would count something which is not really Tennessee warbler or which is not really there, we say that's not possible, we are good birders. And so we are just looking at the 1s, 2s, and so on, and how when we have an indication of the species being there, how that count is divided across the time intervals. So the conditioning mean that we are pretty sure the species was there, and if we condition on the total, then we are removing the effect of total abundance. So if it's half of 2 or half of 4, that's still the same proportion and is going to lead to the same kind of curve for phi, right? So that's what we are doing here as part of this conditioning, and that's why we are using conditional maximum likelihood. And this makes it also really fast, because we've seen only 5% of lots of data is actually non-zero. And the zeros, when you see 0, 0, 0, that is not helping. That doesn't contribute to the likelihood, so we might as well not use it at all.
Okay.
So that was kind of our thinking when we came up with this. And that's just another reason I'm often looking at hundreds of thousands of surveys, and this just helps making those estimates a bit more faster. So about mixture models, let me just find that HTML docs 2.4 web browser. So we have some of the same things, processing the data again, Tennessee warbler as before. So we kind of continue with, we already have these 3 models, the null model, day, time since sunrise, and a little bit of a simulation. So what we do here in these finite mixture models, and maybe I can use this graph to get the point across, is we suspect that not all the individuals are behaving the same. So when I'm just looking at a single survey, a single landscape, and there are, say, 50 individuals, maybe 20 of those is going to vocalize like crazy because they're still looking for a mate. And the rest, maybe at the time, they're settled, they're good, they're not vocalizing that much. So there might be different groups in the same population. And once you look at their data, it might be kind of a mix of the two. And you need to know two things. What is their fee? So how often they do their behavior events, and what is their proportion? And so we've seen how to estimate the rate. And now if you assume that the intercept where this line is starting from is not 0, so before we had the line start at 0, now it's somewhere higher, 25%. This intercept is going to be defined by the proportion of the two groups. So we can say, oh, I didn't include this. So there's an image missing from the notes. So this was our image before, and this is now. When we have two groups, one group, those are the frequent singers. You can see ... lots of dots. That means those events happen at a faster rate. And these are the lazy birds. They're just vocalizing as usual. So if you have a mix of these two, that's when you might need a finite mixture model. And by finite, I mean there's a known number of group, which is not too many. In this case, it's two: frequent singers, infrequent singers. And if that's the case, you can parameterize that as the usual conventional model plus this intercept thrown into the mix. So that becomes, you have 1 minus C for the heavy singers, and then C times 1 minus e to the power, the usual stuff. These are the infrequent singers, which reduces to this 1 minus C times e to the power minus time times phi. So this is the cumulative density function we see here, the red line. And if we know this cumulative density function, again, we can fit this model to the data, and that's what is happening when you use this F-mix, finite mixture, as the type. Same thing, Y, pipe D follows 1, so it's just a constant. But the output is now showing us there's a phi and the C and the logit of C, because that's between 0 and 1. So without going a lot more into the details, this is kind of the finite mixture model that we can also fit. And there is also a time varying version of that. Actually, two time varying versions, because now we can say phi is a function of time or C is a function of time, which is a slightly different interpretation. If you use F-mix, that means phi is going to be a function of day and C is constant. And this is how you can think about it. Over the season, that phi is higher or lower, but the intercept, which relates to the C, is the same. The other interpretation, which in case works a bit better, is to use mix without F. And that means phi is constant, but C varies by day on the logit scale. If you make the prediction, you see intercept is changing. It's higher early in the season, lower late in the season, and the slope, that phi, is constant. So you see this rainbow. And if you compare all these conventional removal models and all kinds of mixture models, then we can see MM1, which is the mixture model like this, where the intercept was changing over time, was the best. But if you look at this probability of availability, and if I scroll back and you recall the third graph that I showed you a few minutes before, there's not a lot of change. So really, when you make availability not at 1 minute, but at 3, 5, maybe 10, then this probability is not going to vary a lot, because this part of the curve is not changing that much. You still see it's higher here, lower there, and kind of the probability values are not super different. So it's not like 0.2 in one case and 0.8 in the other case. And so even though this model is the best, often with species with a less number of detections, we find the plain simple exponential model to work really well, because there we need to estimate less unknowns, and as a result, it's just going to work for those species where we don't have a lot of detections. So this was all real data, and now we can go back and look at how to estimate abundance.